Hello everyone. With this video I want to talk about how intermolecular forces can affect certain properties of compounds or molecules in compounds, I suppose. So what I want to do is talk about how melting point and boiling point, let's talk about this first. So if we talk about the point at which something melts, at the point at which it boils, those are going to increase with increasing intermolecular forces. So it doesn't matter what kind of intermolecular force we have or IMF we have here. What matters is that the fact that if I have stronger IMFs, it's going to take more energy to break those bonds. So if it's going to melt, that melting point will now be higher. If it's going to boil, that boiling point will be higher. Okay, why? Because it takes more energy to break those attractions to move to the next phase. Okay, so that's melting point and boiling point. Now, related to this is something called heat of vaporization. And heat of vaporization is the amount of heat it takes to transform a liquid to a gas specifically. Okay, so when we're talking about HVAP, what we see here is the amount of heat it takes to do this. Well, if the forces of attraction are stronger on the molecules in a liquid, they're more strongly attracted to each other. If they're more strongly attracted to each other, it's going to take more energy to break those stronger attractions. So increased IMFs gives us increases in delta, or in the heat of vaporization. Okay. The next thing I want to talk about is, again, vaporization, a continuation of this, I'm sorry. So it changes from liquid to gas. This is, of course, endothermic. Okay. You need heat to go in to make this thing happen. If you think about sweating, it does take quite a bit of energy for you to break the water molecules' intermolecular forces, in this case, the hydrogen bonds of the water on your skin. So you provide that energy to break those attractions, and therefore that's the dissipation or the movement of heat from your skin to the liquid, which is water in this case, to break those attractions, and that gets carried off. Okay. Now, vaporization can be a slow process because vaporization only happens at the surface of the liquid and the air, that interface. Okay. And not only that, but the second thing is those particles must have enough energy at the surface. So if we take a look at, let's say this is room temperature right here, this is 25 degrees Celsius, and this is, let's say, 100 degrees Celsius. This is another Maxwell-Boltzmann energy distribution diagram. So if this is 25 degrees Celsius, only these particles at the very tippy top have enough energy to break into the gaseous phase. And these particles have to be at the surface. So this small fraction of particles here is the only stuff that A, has to be at the surface, and B, has to have enough energy to evaporate. That's why this is a slow process. You'll see that at 100 degrees Celsius, all of these particles are available to evaporate, okay, or at least a higher temperature. I don't know if it's 100 degrees Celsius, but anyway, okay. So the next thing is viscosity, and the viscosity is the resistance of liquids to flow. So real thick or high viscous fluids with high viscosity is like honey or maple syrup or something like that. Things with low viscosity is like alcohols, water, stuff like that. So the higher the viscosity, the slower something flows. So the greater the attractive forces, the higher the viscosity. Why? Because the particles are more strongly attracted to each other. Okay. An exception of this might be water, where it has extremely high intermolecular forces, but the particles are very small. Okay, they have a very small electron cloud, and they don't get tangled up very much either. Okay, so viscosity can be affected by intermolecular forces. The next thing would be surface tension. And with surface tension, this is the skin on the outer surface, again, the liquid to air interface. Okay, so if we have a greater IMF, so if IMFs are greater, therefore these particles again are more strongly attracted to each other. I keep saying that over and over again. With the greater attractions, the stronger the skin, the greater the surface tension. Water has a good surface tension. You can actually rest pieces of metal on the surface of water because of that attractive force is so strong and forming a very tight skin. Okay. Something like alcohol, which has a weaker intermolecular force of attraction, is still hydrogen bonded, but a weaker form of it, a weaker version of it. It's impossible to get things to like a needle to rest on the surface of that liquid just because of the weaker forces of attraction. Okay, so we'll go over a little bit of this in class, but the viscosity of a liquid is dependent by the strength of the intermolecular forces. Okay, so if you take a look at this chart here, you'll notice that the type of attractions is compared to the viscosities as far as what we've been talking about, little things like this and there. Okay, so check that out. A couple questions here, which the following is not true regarding the liquid state. Not true regarding the liquid state. There you go. Which of the following is true regarding viscosity? Okay. Which of the following liquids be most expected to have the highest viscosity? The highest viscosity. So again, I'm looking at types of intermolecular forces here. I see some polar things, some non-polar things. You're looking for hydrogen bonding versus dipole-dipole versus LDFs. That's the correct answer. Which of the following make gases unsuitable to be used in hydraulics? So hydraulics is using water to um, push large things, grab a hold of things. So hydraulics is used in different machinery to move big things. Okay. Okay. The next thing would be vapor pressure. Okay, so vapor pressure is also affected by intermolecular forces. And basically, vapor pressure is simply the pressure of a gas that has come from a liquid. So if we take a look at this, we look at initially with this vapor pressure here, okay? If we take a look at this vapor pressure, there is the start of vaporization where it happens, okay? Then some of the particles are evaporating and some of them are condensing, and now we have an equilibrium vapor pressure where the two are happening at the same rates. So what is vapor pressure? It's the particles all up in here above the liquid in a sealed container, and it's the pressure that they're exerting on the sides of the container. Okay. Now, this has to do with intermolecular forces and temperature. The higher the temperature, the greater the equilibrium vapor pressure. The lower the temperature, obviously, the lower the equilibrium vapor pressure. The higher the intermolecular forces, the lower the equilibrium vapor pressure. Okay, so now we're comparing two different things, two different compounds or molecules. The stronger the attractive forces, the weaker that vapor pressure is going to be because the particles are more sticky and they have not as many of them have escaped the liquid phase into the vapor phase. So when we take a look at particles that are volatile or, in other words, that evaporate readily, the volatility is, again, I was just talking about this, setting up an equilibrium vapor pressure, temperature, the hotter, the more volatile. Okay, but then we look at intermolecular forces. The weaker the intermolecular forces, the more volatile that it has, the higher the equilibrium vapor pressure. Okay, and vice versa. The stronger the intermolecular forces, the more those particles aren't going to evaporate, or I should say the less they evaporate, and the less we have vapor, therefore a lower equilibrium vapor pressure. Okay? We'll go over this in class, and I believe that's it. Okay? So again, if you have questions, email, talk to me in class when we're online. Either way, we'll make it work.